Okay, there is the cross product, which is written like the vector A cross the vector B. And then there's the dot product, which is written like the vector A dot the vector B. It's important to know that these two symbols, the cross and the dot symbols, mean the same thing when multiplying scalars. That if I wrote 3 cross 4 or 3 dot 4, those would both be scalar multiplication. There's only one type of scalar multiplication. So right away, an important difference to know about the two is that the cross product results in a new vector C, and the dot product results in a scalar D. Okay? Now I want to talk about some properties. Okay, the cross product likes, in parentheses, perpendicular vectors. What I mean is, if you have any two vectors A and B, if they are perpendicular, your cross product is going to be the largest value that it can be. Okay? As they become less perpendicular, the value of your cross product is going to decrease in magnitude. And then finally, if they are parallel, the cross product is going to be 0. Okay, the cross product of any two parallel vectors is always 0. The reverse is true for a dot product. Dot products like parallel vectors. So if you have any two vectors A and B and they are parallel, the dot product is going to be the largest possible value. And then as they become less and less parallel, that value is going to decrease. Finally, if they are perpendicular, the dot product will be what? What do you guys think? 0. Okay? Perpendicular. Here. Okay, the dot product of any two perpendicular vectors is always 0. So if I were to give you two random vectors, let's say A was I minus 3j, and B was 4I, say 6I, plus 2j, and I were to ask you to describe the relationship between these two vectors. A, the vectors are parallel. B, the vectors are perpendicular. C, the vectors are neither perpendicular nor parallel. Or D, none of the above. Okay, let me write this down. So describe the relationship between A and B. A, they are parallel. B, they are perpendicular. C, They are neither parallel nor perpendicular. I just write it as perp because I don't want to write out the entirety of perpendicular. Or none of the above are true. Okay, first of all, I hope you guys realize that D is clearly not correct. Vectors have to be parallel, perpendicular, or neither. There is no fourth option. Okay? So sometimes I will just run out of options and I'll throw in one that cannot possibly be correct. So give it a look over before you choose an answer, because sometimes you'll run into this kind of situation. So this cannot possibly be correct. You can use the dot product, A dot B, to determine whether they are parallel or perpendicular. You could also use the cross product to determine whether they're parallel or perpendicular. If you take the dot product and it's 0, what is their relationship? They're perpendicular. If you take the cross product and it's 0, what's their relationship? They're parallel. What if you take the dot product and the cross product and neither of them are 0?
They're neither parallel nor perpendicular.
Then they're neither parallel nor perpendicular. So you can easily investigate the relative direction of these two vectors. Not the absolute direction. A points in some direction on its own. That direction is not relevant. B points in some direction on its own. That direction is not relevant. It's their relative directions. That if A points here and B points here, they have an angle between the two of them. That's the angle that's going to matter when you're trying to compute cross products and dot products. Okay? Right, for the cross product, there's one other thing I need to point out. The cross product, the output is itself a vector, and the output is perpendicular to both input vectors. So the vector C has to be perpendicular to both A and B. This limits dramatically all of the possible directions that C can point. What if I were to say that A pointed here and B pointed here? They're not parallel, so the cross product's not going to be 0. They're perpendicular, let's say, though the angle doesn't matter. If they're perpendicular, then it would be the largest possible cross product. But no matter what the angle is between the two of them, vector C, where C is A cross B, vector C must point perpendicular to both A and B. What directions would be perpendicular to both A and B? What possible directions would be perpendicular to both? Something that's important to know about vectors is that any two vectors form a flat two-dimensional surface, a plane. We talked about this before. What? What were we saying?
3D.
You pointed in some direction?
Yes.
Into the board?
Yes.
Into the board would absolutely be perpendicular to both A and B, but so would out of the board. Those are the only two possible directions that are perpendicular to both A and B. Into the board or out of the board. I'm going to draw that in a second. Those are the only two possible directions. This must be either into the board or out of the board. So, worst case scenario, you have a 50-50 chance of guessing what direction the dot product points. It definitely has to point along the line that travels straight through the board. It either points out of the board or it points into the board. Okay? Any two vectors that you choose, we talked about the idea of completing the parallelogram. So if you were to have A and you were to have B, you could imagine transporting A from here to here. This is A. And you can imagine transporting B from here to here. A is a little bit long, but B transports from here to here. And that is going to form a parallelogram. I can shape this in. That's a two-dimensional surface like a piece of paper. And the output of the cross product must be perpendicular to that surface. It must be perpendicular to this piece of paper. Okay? So if I have a vector A that points like this, and I have a vector B that points like this, I can imagine taking my sheet of paper and completing that parallelogram. Okay? So now my sheet of paper defines that two-dimensional surface, and the vector C must be perpendicular to that surface. It can either be perpendicular up, or it can be perpendicular down. But those are the only two possible directions. There are no other directions in three-dimensional space that's perpendicular to the sheet of paper. Just choose something like this. This is not perpendicular to the sheet of paper. The angle between this and the paper is clearly less than 90 degrees. If you look here and I draw a vector like that, this angle right here is less than 90 degrees from this sheet of paper. Okay? If I were to draw it like this angle is clearly less than 90 degrees from that sheet of paper. So there are only two possible directions that are perpendicular to both. Either out of the board in this case or into the board. Okay? Any two vectors form a parallelogram, which is a two-dimensional surface, and in 3 dimensions, there are only two directions that are perpendicular to a two-dimensional surface. Away from it or towards it. Okay? Any questions? There are going to be 2 ways to do these multiplications. For the dot product, we can use magnitude and direction form, or we could use component form. For the cross product, same thing. We could either use magnitude and direction form, or we could use component form. The dot product is inherently less complicated because the output is a scalar. Because the output is a scalar, the process to do the dot product is inherently less complicated because you don't have to worry about the direction of your answer. Both of these forms are relatively simple to do, so I will show you guys how to compute the dot product using either of those methods. Okay? The magnitude and direction form, if you know the magnitude of A and you know the magnitude of B, and you want to take the dot product of A and B, then A dot B is going to equal the magnitude of A times the magnitude of B times cosine of theta, where theta means something very specific here. As far as this equation is concerned, theta is specifically the angle between the two vectors A and B. Okay? It's not the direction of A on its own, nor is it the direction of B on its own. It's the relative direction between the two. Remember, when I have some vector A, I don't care what direction A points on its own. When I have some vector B, I don't care what direction vector B points on its own. I am investigating whether or not these vectors are parallel or perpendicular. So what I care about is the angle between them. This is the angle between A and B. But you can find that angle if you know the direction of A and you know the direction of B.
Don't have to necessarily be touching, right?
They don't have to be parallel.
Yeah. I mean.
What do you mean touching?
Okay, well, like perpendicular, they don't have to necessarily be.
No, they don't have to be perpendicular, they don't have to be parallel. This works for any angle between them. Okay? So if you were to have vector A pointing in any random direction and vector B pointing in any random direction, they would always have a single angle that described how far apart they were from one another. That's the angle that goes into the cross product. Yeah?
How do you find it?
Can you speak up a little?
How do you find that angle?
So it depends on the situation. But imagine that this was X, and this was Y. You need to do a little bit of geometry. Let's imagine that A had an angle counterclockwise from the x-axis of 45 degrees. And imagine that B had an angle clockwise from the negative y-axis of 20 degrees. How do you guys think you would find the angle between them?
45 plus 90 plus 70.
45 plus 90 plus,
No, it had to be.
okay, where did you get the first 45? Let me change this a little bit. I want to be really clear. I want to make this 40 degrees. Okay? I know that you know what you're doing, but now instead of 45 plus 90 plus 70, it would be what?
It would be easy.
50 plus 90 plus 70, okay? So what she did was she found this angle right here, what's called the complement of 40. Complementary angles add up to 90 degrees. So this piece right here is 50 degrees because the green angle and the red angle have to add to 90. This angle right here is just 90 because it's a full quadrant. And then this angle right here is the complement of 20, which is 70. So if I said the blue angle was the angle we called theta in that equation, then theta would just be 50 plus 90 plus 70, which would be something.
210.
210? I'm going to take your guys' word for it. Remember that I'm terrible at arithmetic. Okay? There's no surefire way for me to tell you how to always find the angle, but it's always going to be some pretty simple geometry like this. Okay, another example, what if this was X and this was Y, and this is A, and this was 10 degrees, and this was B, and this was 70 degrees. Both measured counterclockwise from the x-axis. What would the angle theta in between them be? 60, right? It would be 70, which is this angle, minus 10, which is this piece. So 70 minus 10 is 60 degrees. Okay, so it's just going to take a little bit of geometry, but it's always doable.
Right.
Okay? The point is that you are not concerned when you're considering theta. You are not concerned with the direction of A on its own or the direction of B on its own. You don't care about those numbers as far as theta is concerned. This number and this number are not what you care about. You care about the angle between the two vectors. Okay? Any questions? Yeah.
So that's the angle. What about A and B?
Those are the magnitudes. A is the magnitude of the vector A. B is the magnitude of the vector B. Okay? Actually, I should have typed this picture up. Okay. I'll just leave all that up for now. Okay? So if you're given the vectors A and the vectors B in a magnitude and direction form, if I told you that A had a magnitude of 3 and pointed at 10 degrees counterclockwise from the x-axis, and B had a magnitude of 7 and pointed 70 degrees counterclockwise from the x-axis, then you would have all the information you needed to compute the dot product in magnitude and direction form. You'd know A, you'd know B, and you can easily find theta. But what if you're given A and B not in magnitude and direction form, but what if you're given them in component form?
Convert it.
You can.
Well, you don't have to convert it, you could do that, but there's a component form equation. The component form equation is A dot B equals AX times BX plus AY times BY plus AZ times BZ, if you have a Z component. For the most part, we are going to deal with two-dimensional vectors. So for the most part, they won't have Z components. Okay? Like all the vectors that I've talked about so far have been two-dimensional. They have not had Z components. Okay, but just in case, I included it there.
The component would be like a third line.
If the
Like that third
vectors
line.
had something like plus 2 k hat. K hat is the unit vector in the Z direction. And this one was like minus k hat. If you had something like that, where the vectors pointed in 3 dimensions, then you would need to include the Z components. Okay? But for the vast majority of applications, like 99.999% of the problems, you're not going to worry about a third dimension. Okay, in physics 2, you'll have a few problems that are 3-dimensional. Vast majority of problems in physics 1 are 2D problems. Okay? You also have magnitude and direction and component form. I'm going to give myself a little bit of space here. You also have magnitude and direction and component forms of the cross product. The problem is that the cross product is just more complicated because it has a direction. The direction complicates things. First and foremost, the component form is an extremely complicated process to calculate the cross product, and we are not going to do it. Not going to worry about this. It's a very complicated process, and we're just not going to concern ourselves with it. We're going to stick with the magnitude and direction form of the cross product. The one thing to know about the magnitude and direction form of the cross product is that it is limited in the amount of information that it gives you. All vectors are composed of 2 pieces of information: their magnitude and their direction. If A cross B is some new vector C, then C has a magnitude Okay? And it has some direction. For example, if it was in the first quadrant, we could draw the direction like that. This is just for illustrative purposes. Okay? The magnitude and direction form of the cross product will only give us the magnitude of C. It will not tell us the direction of C. Okay? So as far as we're concerned in this class, we will not have any surefire method for finding the direction of a cross product. All we will be able to figure out in this class is the magnitude of the cross product. But remember, there are only two possible directions for the cross product anyway, right? If A and B are in the board like this, A is drawn in the plane of the board, B is drawn in the plane of the board, then the board itself is that 2D surface, so C would have to point out of the board or into the board. So it's 50-50 which way it points. Okay? The main application of the cross product, which I'm going to illustrate in a minute, is a quantity called torque. And when we're using torque, we will not care about the direction of the torque. Okay, and I'll explain that when we get to that in a later chapter. Okay, it turns out that trying to find that direction is complicated and it won't be particularly useful. We won't need it. Okay, so we just won't worry about it. Okay? So I'm going to write the magnitude and direction equation in a very specific manner. And I want you guys to understand what I'm writing here. The cross product is written as A cross B. But what is A cross B? It's some vector C, right? I'm not finding the entirety of C. What part of C am I finding? The magnitude. So I have to modify the left-hand side here. I'm going to put equals and something here. What's on the right-hand side is going to be a scalar because the magnitude is only a scalar. But the left-hand side, as I have it written, is a vector. So what I'm going to do is I'm going to put the absolute value bars, because now what that's saying specifically is this equation tells me the magnitude of A cross B. That's what that is. That's the magnitude of A cross B. It's not A cross B in its entirety. Okay, and what it's going to be is it's going to be the magnitude of A times the magnitude of B times sine of theta. Okay? Where theta is defined the same way. Theta is the angle between A and B. Okay? The behavior of A dot B is determined by cosine, and the behavior of A cross B is determined by sine. And that behavior perfectly encapsulates these rules that I told you. Okay? What if you had two vectors that were perpendicular? Their angle of separation, theta, is what? 90 degrees. If I calculate the dot product, what is cosine of 90? You guys have a calculator. If you want to just put it in. What is? What?
1 or 0.
It's going to be 1 or 0. For cosine, it's 0. Okay? On the exam, you guys have a calculator, so you don't have to just guess. You should definitely plug it in. But the cosine of 90 is 0. So what is the dot product of two vectors that are perpendicular? 0. Cosine of 90 is 0, so the dot product is 0. Like I said, it likes parallel vectors, so the dot product of any two perpendicular vectors is always 0. And you see that behavior from the cosine right away. Now let's look at the cross product. If they're perpendicular, then that angle is 90 degrees. And what's sine of 90? 1. What is the largest value that sine can get? Can sine get any bigger than 1?
No.
No. Sine is going to be between the 0 and 1. Okay? So the cross product likes perpendicular vectors. When you have two vectors that are perpendicular, the output is the largest it could possibly be. A is going to be a fixed number. B is going to be a fixed number. It's just how long the vector A is and how long the vector B is. Their angle can change, but by changing the angle, you're not going to change the lengths of the vectors, right? But when you make them perpendicular, all of a sudden, your cross product is the largest value it could possibly be, because sine of 90 is 1, and 1 is the largest output of sine. Any angle less than 90, sine is going to be less than 1. Okay? So that sine behavior perfectly encapsulates the liking perpendicular vectors aspect of it. Okay? What if we chose two parallel vectors? What's the angle between them? 0. What's cosine of 0? 1. Cosine of 0 is 1. Okay, the dot product likes parallel vectors. Can cosine ever get larger than 1? No. If you had any angle greater than 0, cosine would be a number less than 1. So when they're exactly parallel, the dot product is the largest value it will ever be. And it's because dot products like parallel vectors. On the other hand, if we go to the cross product for two parallel vectors where their angle is 0, what's sine of 0?
0.
0. So the cross product of any two parallel vectors is 0. And it's because the cross product likes perpendicular vectors, so the cross of any two parallel is always 0. That behavior of the cross and dot product, that behavior is entirely encapsulated in these magnitude and direction equations. Okay? Any questions? All right, let's answer this question right here. Are they parallel? Are they perpendicular? Are they neither parallel nor perpendicular? The vectors are given to us in component, so let's do the dot product in component form. You have two equivalent ways of calculating the dot product. Both of these should give you the exact same answer. So which one do you choose? In any given problem, should you use this equation or this equation? It doesn't matter, but the amount of time it takes to do them will be affected by your choice.
Magnitude direction would be shorter.
Hmm?
The first one would be less time.
The first one would not be less time for this question. The first one would be more time because you have to convert these into magnitude and direction form.
Okay.
Say it again? It would be component form, but how do you know to choose component form? Because you already have it in components. Go with whatever the question gives you. If the question gives you them in components, use component form. If the question gives you the vectors in magnitude and direction form, use the magnitude and direction form. Go with what the problem gives you. Okay, but they are absolutely the same. And I'll show you in a moment that we'll calculate the component form and we'll get, actually, I'll do a different problem and I'll show you that they're equivalent. These two vectors I specifically chose because they are going to be perpendicular. Okay? But let's calculate the dot product. The dot product of A dot B is going to be AX times BX plus AY times BY. We don't need to worry about the Z components because they are 0. This is plus 0K and plus 0K. Okay? So AX is 1, BX is 6, plus AY is negative 3, by is 2. So this is 6 minus 6, which is 0. Therefore, the vectors are,
Parallel.
if the dot product is 0, the vectors are what? Perpendicular. Dot product likes parallel vectors, so if it's 0, they are perpendicular. Okay? Any questions about this problem? Yeah.
You can also just look at the slope for the formulas, and you can see that over there is res over I, which is negative 3 over 1.
Yeah.
And then the bottom one would be 1 over 3, which is
Yeah, so their inverse tangents would be complementary. They'd add to 90. You could also do it like that. Absolutely. Two-dimensional vectors, you could also find the angle of one and the angle of the other, and you can see that their angles would add to 90. Absolutely, you could do it that way. All right, let's imagine now that I had two random vectors. I didn't choose them specifically to be. So what I want to say is compute the dot product A dot B, where A is 2I plus 3J and B is 4I minus J. They're given in component form, so the simplest way to compute the dot product is to use which equation? The component form equation, right? So we'll say that A dot B is AX BX plus AY BY. AX is 2, BX is 4, AY is 3, BY is negative 1. By the way, this should always be a plus sign. It should always be a plus sign. The negative sign here is brought in as negative 1 into the y component of b. Okay, this should always be treated as a plus sign. 2 times 4 is 8. 3 times negative 1 is negative 3. So 8 minus 3 is 5. Alternatively, we can compute the magnitude and direction form of each of those two vectors. So the simplest thing to start with is to find the magnitude of each vector. If we know the components, how do we find the magnitude of a vector? The Pythagorean theorem, always the Pythagorean theorem. So A is going to be the square root of ax squared plus ay squared, which is the square root of 2 squared plus 3 squared. So 4 plus 9, 13 square root is 3.61. Magnitude of b is the square root of bx squared plus by squared. Bx is 4. Remember that in the Pythagorean theorem, this is also always a positive sign. The fact that by is negative 1, when you square negative 1, it's going to become positive 1. So you can just ignore the negative sign. This is just plus 1 squared. That negative sign squares away. So it's 16 plus 1 is 17. Square root is 4.12. Okay? So we know the magnitude of each vector. Now we have to find the direction of each vector. And we're going to use that approach, that two-step approach that I always said. We'll draw the vectors, we'll define their directions to the nearest x-axis, and then we'll use the inverse tangent of the absolute value of the y component over the x component. So A is positive 2 in the x direction and 3 in the positive y direction. So A is in the first quadrant. Right? B has a positive x component but a negative y component, and that's in the fourth quadrant. Okay? Remember that angles are typically given by Greek letters. So I'll call the angle for A alpha, which is the Greek letter for A. And I'll call the angle for B beta, which is the Greek letter for B. And both of those angles, because we chose them to the nearest x-axis, they will both be given by the inverse tangent of the absolute value of y over x. Okay? So alpha will be the inverse tangent of the absolute value of ay over ax, which is the inverse tangent of ay is 3, ax is 2, over 2, inverse tangent is 56.3 degrees. Okay? Beta is going to be the inverse tangent of the absolute value of the y component over the x component. Always of this form. Remember that finding direction is a two-step process. The first step is to always choose your angle to the nearest x-axis. That guarantees that your equation will always be the inverse tangent of the absolute value of y over x. Okay? So the inverse tangent of the absolute value of the y component is 1. And the x component is 4. Over 4, inverse tangent is 14.0 degrees. Okay? So now I want to call their angle of separation, the angle from A to B, I want to call that angle theta. What should theta be? What? Yeah, it should be alpha plus beta, right? It should just be the sum of those angles. So theta is going to be alpha plus beta, and that's not always true. That's true in this case because of how the geometry worked out. Pictures are always worth drawing for vectors because vectors are geometric objects, and it will help you visualize what's happening. Alpha is 56.3. Beta is 14, so 70.3. Almost done. Now we can do the dot product using the magnitude and direction form. We know the magnitude of A, we know the magnitude of B, we know their angle of separation theta. So the dot product A dot B is magnitude of A is 3.61. Magnitude of B is 4.12, and its cosine of 70.3 degrees. .61 is 4.12 is 5.01.
Alpha in this case, you're referring to vector A.
Yep. It's the angle that I declared for vector A, just the direction for A. Angles are typically given by Greek letters,
Right.
and I couldn't use theta 3 times.
Right.
So I just said alpha is a Greek letter for A, so that'll be the direction for A. Yeah.
What's that 5? What's that 4?
So this is 5.01, and the squiggly lines, that's approximately equal to.
But like the length?
Oh, this 5, no, that's the value of the dot product. I'll talk about what the dot product represents right now.
Yeah.
Okay? So we still have 15 minutes left in class, or 20 minutes-ish. So I'll probably just finish today's class by talking about what the dot product and cross products represent. I don't want to get started on chapter 2 with like 5 minutes left. Yeah. It would be 5. Because the answer is exactly 5. If I do the dot product in component form, the answer is exactly 5. If you were to get 5.01, I'm not going to include 5.01 as one of the possible answers. I'd include like -3, 5, 7, or 9, which are all like well separated. That wasn't the question. The question was compute the dot product. I don't know that it's neither parallel nor perpendicular. Okay, actually I do, because I calculated the angle between them. The angle between them is 70 degrees, so it's neither parallel nor perpendicular. Right, if it was parallel, the angle would be 0. If it was perpendicular, the angle would be 90. But the question was compute the dot product. It was a different question than this problem. Okay? Yeah.
When you ask to compute the dot product,
Sorry, can you speak up a little?
when you ask to compute the dot product, you could just choose either one. You don't
Just
have to
choose
do
one.
right.
I was just trying to show you that they're the same.
Okay.
Absolutely. On the exam, if you're asked, or in the homework, if you're asked to compute the dot product, just choose the easiest one. Look at how this separates. This is the question. This is answer 1. Computing the dot product in the convenient form, and then the rest is answer 2. Computing the dot product in the inconvenient form. So computing the dot product in the convenient form is much quicker. You do that and then you're done. I'm just trying to show you that they give you the same answer.
The red one would be component form. So the first one is component form, I see that.
Yep. The second one is magnitude and direction form. The vectors were given to you in component form.
Right.
So it's quick to compute the dot product in component form.
But in this case, you converted it.
I want to show you that they're both the same, so I converted it from components into magnitude and direction. Here's the magnitude of A, here's the direction of A. Here's the magnitude of B, here's the direction of B. And I wanted to show you that if you converted it to magnitude and direction form and used the magnitude and direction form of the dot product, you would get the same answer. There's a rounding error, right, of 0.01, which is like a fifth of a percent off. So it's 0.2% off. All right, so it's almost exactly the same. But there's a slight rounding error here because I rounded these answers and I rounded these conversions. The answer is exactly 5. Okay, there's no rounding involved in this computation of 5.
Quick question.
Yeah.
If it's given in component form, we would never have to use dot product. It doesn't make sense. You could just plug it in component form.
No, you will have to compute the dot product. That just did. But there's no point in computing the dot product this way, in the magnitude and direction way. There's no point in doing it that way because it's much easier to compute it in the component method.
Right.
Yeah.
So it wouldn't make sense to use the dot product if it's given like component form, right?
Exactly.
No, the question just said compute the dot product.
Right, but we wouldn't have to if it's given that way. We could just
This
put it in.
is not given as part of the question. This is the first answer. The question stopped here. So the question said compute the dot product if this is A and this is B. The question is not going to ask you to compute the dot product and also give you the dot product. Because then there's no point in doing anything, right? You already have the answer. I'm trying to illustrate that there are 2 ways to answer this question. The first way is very, very simple because it's the natural way given the information. The second way is also possible and it gives you the same correct answer, but it just takes a lot longer. Yeah.
The second one is always gonna be longer, or it's just?
If the information is given to you in magnitude and direct component form.
How is it gonna look for the second one? How is it gonna look?
I could give you a question where the vectors were given in magnitude and direction form instead. What if I told you that you had, so I want to say compute A dot B if the vector A has a magnitude of 3 and makes an angle of 40 degrees counterclockwise from the x-axis, and the vector B has a magnitude of 4 and makes an angle of 10 degrees clockwise from the negative x-axis. Both of these vectors are given in magnitude and direction form, so we will use the magnitude and direction form of the dot product to compute it. We know A is given to us directly. We know B is given to us directly. The one thing that isn't given to us directly is theta. Yes, but we can find it, right? What will that angle be? How will we find it?
180
Uh-huh.
minus 50.
Exactly. This theta can be found by saying that 40 plus theta plus 10 has to add to 180. Okay? So this would be 180 minus 10 minus 40, which is 130, I want to say. Okay, now we know A and B and theta, so we can go ahead and compute the dot product. A dot B is just A times B times cosine of theta. A is 3, B is 4, and cosine of 130 degrees is negative 7.71. You guys should, on your own, convert these vectors into component form and then do the dot product in component form and get negative 7.71. You guys should do that on your own to make sure that you get the same answer. Okay? Any questions? All right, there are two quantities that we're going to talk about later on in the class. One is known as work, and one is known as torque. Okay? Work is given by a dot product, and torque is given by a cross product. Okay, let's start with the idea of work. Work has to do with energy. It has to do with a specific energy called kinetic energy. All objects have a kinetic energy depending on how fast they're going. Okay? So if I take my bag and I place my bag here, how much kinetic energy does it have right now?
0.
None. If I move it, now it has some non-zero kinetic energy. We can say it has a kinetic energy of 1 or 2. The number doesn't matter. Kinetic energy is always positive. So it's either 0 or it's greater than 0. Okay? Work, W equals the change in kinetic energy. So my bag has how much kinetic energy?
None.
When I push it, how much kinetic energy does it have now? Some positive value. Did its kinetic energy change?
Yeah.
Yes. It went from 0 to some value above 0. So some work was done. Work was done by the force of my push. So by pushing the bag, I did work on the bag. It had no kinetic energy. Now it has some kinetic energy. So I did work on the bag. Delta, this symbol here is a really, really common symbol that appears in physics and really appears in all sciences. It always represents a change in something. You guys should get comfortable reading deltas. Did I see someone? Did you have a question? Okay. First of all, delta represents a change in whatever. Delta K is a change in kinetic energy, and it always equals the final value minus the initial value. So what if you have the case where the final value is greater than the initial value? If the final is greater than the initial, delta, is it positive, negative, or zero? Positive, right? If delta is greater than 0, then final is greater than initial, and your value is increasing. It's rising, right?
Right.
Because your initial was small, your final was large, so your delta is positive. This corresponds to an increase. What if your initial is greater than your final? What if you start high and then end low? Delta is going to be what? Positive, negative, or 0? Negative, right? If your final is less than your initial, this number is going to be negative. So if delta is negative, this corresponds to a decrease. You start high and you end low, and the final minus the initial is negative. What if delta is 0?
Equal.
No change. If your final equals your initial, final minus initial is 0. If your initial is here and your final is here, there's no change and your delta is 0. Okay, these rules are important to know. Okay? I want to show you guys that the work obeys the correct delta rules when you define it as the dot product between the force applied and the direction that the object is moving. Okay? So if you have an object and this object is moving in some direction, the direction of motion, which we will give by a vector that we'll call delta x. This will make more sense. We'll understand what delta x is next time. But for now, just associate delta x with the direction of motion. And the object experiences some force acting on it. Then we will say that the work is computed by F dot delta x. And I want to show that this equation obeys the correct behavior of delta K. So scenario 1, my bag is at rest and I push my bag. So this is the initial state. I have a bag at rest, and I'm going to push it, let's say to the right. Then my final state is my bag moving, still being pushed to the right. So we already know the direction of the push, it's to the right. What's the direction that the bag moved in? To the right, it moved to the right. So its direction of motion is to the right. What is the angle between the pushing and the motion? 0. They are parallel. right? So the angle between the push, which is our force, and the motion, which we call delta x, is theta equals 0. The dot product is given by a cosine, and what's the cosine of 0? 1. Okay? So, f dot delta x, which is going to be f delta x cosine of 0, is going to be a positive number. Okay? So I know from this right-hand side, I know that the dot product should be positive. Now, I want to calculate the work from the left-hand side by using its definition as a change in kinetic energy. When the bag is at rest, how much kinetic energy does it have? 0. Okay? The initial kinetic energy is 0. After it's moving, how much kinetic energy does it have? Does it have 0 or does it have some? That is a positive amount of kinetic energy, right? Kinetic energy final is positive. It has some kinetic energy. So if I wanted to calculate delta K, K final minus K initial. K initial is 0, and K final is positive. So what's delta K going to be? Positive. So you see positive and positive aligns. Okay? I want to consider scenario 2 now. When I push this bag and I give it some energy, that bag will move. But it's not going to move indefinitely, right? If I push it and let it go, what happens to the bag? It stops. It slows down and it loses its kinetic energy until it's back at rest. Why does it stop?
Friction.
Because there's friction on the tabletop. Friction is always going to apply a force in the opposite direction from the motion. Okay, so scenario 2, we'll say that the box is initially moving to the right, and it experiences a friction to the left until it stops. So what's its initial kinetic energy? Positive, right? Because it's moving. What's its final kinetic energy? 0. So delta K is K final minus K initial. K final is 0. K initial is a positive number. So what's 0 minus a positive number? It's negative, right? So delta K is a negative number. And it should be negative because the kinetic energy is decreasing. Now, what about the work? What about the dot product, F dot delta X? This is F delta X cosine of theta. What is theta going to be if delta X is to the right and F is to the left? Nope, it's not 0. If one vector is to the right and the other vector is to the left, what's the angle between these vectors? 180. They point in opposite directions, so the angle is 180. So this becomes F delta X cosine of 180, which is negative. Cosine of 180 is -1, so it's negative. So you see right here that the behavior of work as the change in kinetic energy, this behavior is encapsulated by a dot product. The appropriate behavior is encapsulated by a dot product. What a dot product actually measures is how parallel two vectors are. Okay, when it's an extremely large positive number, the two vectors are very parallel. When it's 0, the two vectors are perpendicular, and when it's a very large negative number, the vectors are very anti-parallel, pointing in the opposite directions. Okay, we're out of time. Next class, I'm going to wrap up by talking about torque and the cross product, and then that'll be it for vectors. Okay, we're going to start up immediately after that, after a 5-minute discussion about torque. We're going to start up with chapter 2, which is motion in one dimension. Okay? Any questions? The chapter 2 homework is already posted. Oh crap, hold on. I keep forgetting. I need everyone to sign in. I'm going to leave multiple sign-in sheets here. Just put if you're the first one signing in, put the date at the top.